So today I skip chapter 3 and chapter 4. Then we are at chapter 5. Okay, so we go from chapter 5. Hopefully this is working. I think this is working. Anyway, so we learn about deformation. Consider a material continuum occupying region B0 with volume V0 and surface area S0 at time t equals 0. At later time t, we see this body in a region B with volume V and surface area S. I'm not sure what's the difference between region and volume. It seems to me it's same. And the surface area S. We refer to these two configurations as undeformed and deformed configurations, respectively. We use a fixed Cartesian system to describe the geometry of the two configurations. As shown in figure 5.1, a generic particle in the undeformed configuration has the position x, and the same particle in the deformed configuration has the position small x. We simultaneously develop descriptions of the geometry of this mapping from the state B0 to B. Using x1, x2, and x3 as independent variables and using small x1, small x2, and small x3 as independent variables to distinguish the partial derivative operator partial in the two systems, we use the Latin indices ijk for the component of small x and Greek indices alpha, beta, gamma for the components of large X. For the indices of the unit vector to match the component of the vectors, we denote E1, E2, and E3 by EI in one system and by E alpha in the other. Thus, x equal x alpha, E alpha, small x is xi, EI. We introduce the partial derivative, partial alpha, partial I. So what was the difference between large x and small x? Figure 5.1. Deformation of a body. Anyway, okay. Lagrangian and Eulerian, Lagrangian and Eulerian descriptions. If we use x alpha as independent variables and x small I as dependent variables, that means small xi is a function of large x1, x2, x3. We have the Lagrangian description of this deformation. The variables large X alpha are called the material coordinates or the Lagrangian coordinates. If small xi are the independent variables and large X alpha are the dependent variables, that is, X alpha equal X alpha, which is a function of small x 1, 2, 3, we have the Eulerian description of the deformation. The coordinates xi are called the spatial coordinates or the Eulerian coordinates. Small x are called the spatial coordinates or Eulerian coordinates. What was large x? Large x are called material coordinates or Lagrangian coordinates. Anyway, depending on the complexity of the differential equations, the boundary conditions and the usefulness of the solution variable, one of these formulations may be preferable over the other in a particular application. For example, in the mechanics of solid, when we load a rectangular, uniformly thick plate, it deforms into a complex curved shape from the simplicity of the initial geometry. We may prefer the Lagrangian formulation for this case. For a fluid flow program, we can observe the flow characteristics through a wind tunnel window. We may not care where the various fluid parameters were at time t equals 0. We may not care where the various fluid parameters were at time t equals 0. An Eulerian approach is often used in a material particle and fluid as it moves with time. In Eulerian formulation, we stand at a special point and observe. We stand at a special point and observe the passing particles. As x and small x are locations of the same material particle, the functional relations equation 5.1 can be inverted. Here, 5.1. I still don't understand the essential difference between large x and small x. As x and location same material particles, the functional relations equation 5.1 can be inverted in the neighborhood of a point x to obtain equation 5.2. This one-to-one correspondence is known as the axiom of continuity. This axiom implies A, the indestructible nature of matter, and B, impenetrability of a matter. Impenetrability of matter. According to A, matter occupying a finite volume cannot be deformed into zero volume, and according to B, the motion of a body carries every material line into another line and every surface into another surface. Motion of body carries every material line into another line and every surface into another surface. A smooth curve cannot be deformed into an intersecting curve. Not sure what is an intersecting curve. Intersecting curve. This smooth curve is something like this. Intersecting curve is something like this. I'm not sure. The necessary and sufficient condition for the existence of the one-to-one correspondence of the functions x, large X alpha, and small xi in a small neighborhood is determinant, and this is very strange. Determinant partial alpha xi is not zero. The displacement vector is defined as the vectorial distance from the initial position x to the final position x small x of a particle. When this vector is considered to be a function of the material coordinates, we denote it by u. And when it is a function of spatial coordinates, we use small u. What is this? In component form, okay, this one, anyway, we probably have to accept whatever it is. This is a condition we have to admit or accept. Accept axiom of continuity. See, we have to accept the axiom of continuity, and this is the outcome. This is a condition that we have to satisfy to accept axiom of continuity. Displacement vector is defined as a vectorial distance. Yes, vectorial distance. This is this. This is this one. What is this one? From the initial position large x to the final position small x of a particle. When this vector is considered to be a function of a material coordinate, we denote it by large U, okay? And when it is a function of spatial coordinates, we use small u. Yeah. In component form, this is interesting. X and X are mixed. Anyway, in component form, U alpha, U alpha, Xi, this is interesting. Huh? Is this so simple? Where for consistency of notation, the Kronecker delta is introduced. Deformation gradients. From equation 5.3 and 5.4 we get. What is 5.3 and 5.4? Yeah, this is like total derivative. This is like total derivative, right? So the equation quantity partial alpha xi and the inverse is partial I x alpha are called deformation gradients. Figure 5.2 shows the mapping of the element of an element dxi, dx1, differentiating equation 5.3 by xj and equation 5.4 by x beta, we see large x, small x, large x, small x, large x. Right? So this is small x. This is large x. And we differentiate that, differentiate this by j. By xj. How do we do this? partial alpha xi dxi dxa dx alpha we place here, maybe we place here this one dxi partial I x alpha. I'm not so sure. So we obtain like dxi equal partial alpha xi dxi partial I xi x alpha. Let us introduce green deformation gradient tensor F and the Cauchy deformation gradient tensor F in matrix form. These matrices are inverses of each other. Oh my god. It should be noted that in the literature, the transpose of these matrices are often used for deformation gradients. Axiom of continuity requires that these matrices be non-singular. The deformation of these matrices are the Jacobian determinant of deformation 5.3 and 5.4. There will not be any problem in distinguishing the Jacobian J from the integer indices. The determinants have the expansions, such expansions, blah blah blah. Deformation gradients. Let me see, I'm pretty much behind, so let me ask Professor Na to make lecture today. Okay?